Hello, my name is William Jackson Klein. I'm in section K-12 of Physics 2212, and this is Lab 4 of Faraday's Law. Some introductory information, main ideas. The purpose of this lab is to gain understanding of Faraday's Law and induced currents by observing the interactions between a conductive tube of aluminum foil and a bar magnet. Some of the main principles are magnetic flux. The formula is shown there. Just the magnetic field times the area in the n-hat direction. In Faraday's law and Lenz's law, the formula is to the right over there. Basically, EMF is the negative derivative of flux times number of loops. And just to preview the results, my experimental time for the magnet to pass through the tube was 1.666 seconds, and the computational time was 13.07. Notes and assumptions. In this experiment, the system was the bar magnet and the aluminum roll. Surroundings were anything else, including the phone and stopwatch. It's assumed that the only forces acting on the magnet are gravity and magnetic force. At first, initial conditions, magnet's in equilibrium as it's not moving. Then right as it's dropped, gravity is the only force acting on it. Then as it goes in the tube, it has the magnetic force acting on it as well. And then once it leaves the tube, that magnetic force goes away. Some sources of error, mostly human error, which could be just by accidentally moving the tube or timing wrong. And there could be some small things in the surroundings that are unaccounted for. Here's some of my data. So the main procedure, basically just drop the magnet with the north end down through a tube of aluminum foil and timed how long it took to get out the other side. My average time was 1.666 seconds. Below are the results for each trial. My mu value was 4.531, which was found in lab 2. Some additional questions. What would happen if the resistance of the conductor was decreased? Since electric potential is equal to current times resistance, electric potential is constant. If you were to decrease the resistance, then the current would just increase and become very large, which would mean that the magnetic force from the current would increase as well, so it would take longer to get through the bottom of the foil. If there were holes or slots in the tube, there would be fewer rings, so there would be less current total, so that there would be less magnetic force, and so the magnet would fall through the tube faster if there were holes or slots. Here's my Glowscript model. This is the velocity versus time graph of the Glowscript model. The black curve right there is the velocity of the magnet at each point in time, and the red curve is the position. Some of the questions. I know that the counterclockwise current in the part of the Glowscript code, which was not shown in the previous slide, the link is in the description though. I know counterclockwise is blue because since the north end is down, the induced current is in the counterclockwise direction, and it appeared blue on the simulation. If you were to flip the magnet around, the magnitudes of the magnetic forces would be the same, but they would be in opposite directions. Like that current would be in the clockwise direction, it would be red. How do the experimental and computational times compare? They are very different. This is because experimentally there are such things as like resistance or other forces that were not accounted for in the code. So if those had been accounted for, the results would be more similar. And what does the shape of the graph tell you about the forces acting on the magnet? I'm looking specifically at the velocity curve. The greater magnitudes of slope at the beginning and the end show that that gravity is the only force acting on it because there is some sort of net acceleration. However, when the magnetic force cancels it out, that slope becomes pretty much zero, which means that it is equilibrium, so the magnetic force is counteracting the gravitational force at that point. In conclusion, I thought this lab was very interesting. It taught me a lot about Faraday's law, and I really gained an understanding of the topic. It was really cool to see a real-life example, and I never would have predicted that the outcome would be the way it was. Yeah, I really enjoyed doing this lab, and it helped me understand the topic a lot better. Thank you so much for your time, and I hope you have a great day.